I'm now extremely sorry that I agreed to chair because I have a million questions for that really wonderful talk. Let's start over here. So, Robert.
I think Kareem is first.
Oh, Kareem.
Thanks. It's only a short question, so it's more...
Actually, can people please hold their hands up? I'm sorry, while Kareem is talking.
It's just really more of just I thought it would be quite interesting to think about things from a different perspective. It would be a different project, I suppose, but like I think about these things in a quite different way, more from Hamiltonian dynamics, and I don't see any reason why you wouldn't be able to do a constrained Hamiltonian dynamics version of the Saunders-Knox space-time. So it'd be, and what would be nice is that you'd also then have it's something like the Barber-Patotti theory with an ability to define rotations. So I don't know if anyone's played with doing this, or we've talked to Ollie about this idea.
Yeah, no, that's a really interesting idea. I mean,
I just don't think there would be any, like, you'd need someone who's good at maths. But
you think you're sort of starting with the Saunders, yeah, so
yes,
your
you could
basic
start
variables
with,
are the relative
exactly, and you could actually
well, yes, it's basically what you do in Barber-Patotti
Sure.
theory, but with a bit of extra, yeah.
So I think that'd be interesting to think.
Yeah, you're right. Well, I'll take that as a helpful suggestion for a 5-year.
Or maybe we can do this on the plane home.
Midnight, yeah.
Now, Robert.
Okay, thanks, that was great, and I don't really disagree with any of it. Just a couple of historical notes. One is, I suppose that being a reasonable person, Simon would have wanted to change the name of Maxwellian spacetime because I think Ehrman gave the spacetime that name on the basis of a quote from Maxwell that I think Ehrman had no idea Newton had said exactly the same thing 200 years earlier. And he was just giving credit where credit was due, including Huygens, who also had a great deal of insight into what conception of relativity was possible at the time. The second historical note is that in his 1977 paper, Stein really placed a great deal of emphasis on corollary 6 and on the limitation of the difference between being able to establish an inertial frame and being able to establish an isolated system, which may or may not be an inertial motion in Newtonian space-time in its classic sense. And the third broader historical note, there might be another way of thinking about the difference between two ways of thinking about space-time. I mean, instead of saying, well, there are two types of space-time structure, I could say, well, I could be thinking about space-time in connection with one or another kind of physical interaction. Right? So in the case of Newton, I mean, there are various reasons having to do with what mathematics was around at the time for his not being willing to get rid of the idea of an inertial frame, or well, an anachronistic thing to say. His not being willing to pass from being able to say we don't know if the whole solar system is accelerating to saying, well, there's no such thing as the absolute acceleration of the solar system. I'm going to mention one of those considerations in my talk, but if you consider what kind of interaction is relevant, Newton, for example, would have had no idea, probably didn't have a fixed opinion on the relation between gravity and light, and whether in a linearly accelerated frame you might notice, in a mechanically accelerated frame you might notice differences in the velocity of light. And Einstein's extrapolation that every kind of physical interaction would have the same behavior in freely falling frames that those interactions observed so far had had, really was a far-reaching extrapolation. It's been very well tested in the past 100 years, I think, but it was still an extrapolation. And so the sort of bare Maxwellian space-time or Newton-Huygens space-time that Simon wanted to outline, well, there are certain kinds of interaction in which it might make sense to think that's the structure of space-time. But if we're considering, as Newton was, always the relationship between the inertial structure and the gravitational field, then your approach does seem like the most natural one.
Quite possibly, although, I mean, I suppose there's also, I mean, whether or not you think Newton-Cartan theory is empirically equivalent to Newton's mechanics might depend on what you think light's going to do in Newton's mechanics. I mean, depending how much you think is, if you think light has to travel in straight lines, or just follow geodesics, right, then it hugely depends on whether you think light's affected by gravity in the original theory.
Right.
I take it
Right.
the kind of the normal modern context just assumes they're equivalent, and therefore assumes that you somehow you set a light theory that had the appropriate kind of symmetries in it, that it would.
And then there's also the asymptotic behavior, right? Because, I mean, Simon's laws of motion don't have the same asymptotic behavior as Newton-Cartan theory. I don't think. I haven't worked that out on paper. But.
Is that right?
Well, for example, the relative
Worries
laws
about
of motion, right? So if you have particles, if you have just one particle, right, then you don't actually have a law of its motion.
So that's true. Yeah.
And you could say, well, we don't need to be able to talk about that, which is fine.
No,
Yeah.
that's absolutely true. That yeah, one particle universe has no dynamics. In some sense. Yeah, I mean, there's lots of sort of very subtle questions about theoretical equivalence here, because there is something funny about the fact that we take theories to be equivalent when their models aren't the same, right? But I'd say something funny is going on when you talk about these theories.
But my general point was just that it's really, it might be less a question of different approaches to space-time
Yeah.
theory abstractly and different ways of thinking about which interactions are fundamentally related to the space-time structure.
Yeah, that's well taken. I think that might be right, although I'm not sure that, for example, the role of light is going to lead. I would have thought that. Obviously, you need to know how light behaves, right? But if light breaks symmetries in certain kinds of ways, that's probably going to do in for both readings. I mean, a very easy way to reinstate.
Well, it did, right?
Yeah, yeah, exactly. But, an easy way to reinstate absolute space, right, would be to have a kind of Galilean theory of light underneath it, right? And then you would vindicate all sorts of things. So it's very hard to. So what I'm having trouble imagining is the behavior of light that might make one conception of space-time look good on this formulation, the other look bad. But I mean, that's a failure of imagination on my point.
So I just want to make sure I have the queue right. So right now I have Chris, then Wayne, and John Doherty. Did anyone else have their hand up that I missed? I'm sorry. So Chris.
Well, I think this is essentially the same question, just phrased less elegantly. But for me, I haven't read David's paper, but the distinction between background and inertial geometry, it wasn't clear to me, and this is partly what dynamics you're thinking of when you say background geometry is just what you need to write down the dynamics, because I think in a lot of cases, once you've written down the dynamics, then you can, in effect, construct an inertial frame. Right? You say, well, if we have a certain kind of dynamics, then I can take 3 particles, and with those 3 particles, I can construct an inertial frame. And so the idea that second structure is new and wasn't already, in fact, implicit in the dynamics is a little mysterious to me.
Good. So I think that's where the talk of emergence might be misleading here. I don't think that David's also really interested, and I think right to be interested, in scale relative. So one of the interesting things about inertial geometry is it ends up being scale relative in interesting senses, and one of the things that he's kind of concerned about is the way in which we can think of, the solar system as a freely falling. The reference frame of the solar system is freely falling, even though we don't describe geometry, and that's sort of from interests he has in GR. So there's sort of that's going on, and that's one of the reasons that he is interested in what he calls emergent inertial structure, emergent space-time structure, but acts the emergent bit, and just, he's not saying that there's sort of lots of work or lots of complicated, it's not that the inertial structure comes out of some kind of complexity. It's just that there's 2 things. There's what's the very minimum stuff I need to have before I can write down the theory. And once I've written down the theory, there are structures inherent in the theory. And
that's what's a little nebulous to me, because if you, I think Robert was pressing on the point that depending on what dynamics or what interactions you include, I could see that if you think of the background structure as something that only includes certain interactions, and then when you add other interactions, then you get more inertial structure. But if you're thinking of one interaction, and you're saying, I want to write down a dynamical theory of that, then in some sense you've also got commitments to inertial structure just in the way you've written down that dynamics, I would think. And so that's why I don't see that there's this sharp contrast, so maybe I'm...
So, I mean, all of this discussion is happening in the context of basically Newtonian mechanics just with gravitation. So that's the dynamics, the gravitational dynamics that are in it. And so I guess the thought is this, that the kind of class of variables you need, so when you write down, you can write down the gravitational dynamics in such a way that it is invariant under the Maximal group. But then you look more closely at what happens when you model systems in that, and you put any kind of realistic solution, and you see that there's this structure. But there was a symmetry of the laws themselves when you wrote them down, before you started thinking about how things behave. That was the Maxwellian symmetry. So I mean, I guess this corresponds to sort of, I mean, what Jim does when he derives the Newton-Cartan structure is he takes all the, he puts in the structure of all the allowed trajectories, right? And of course, in a sense, they're sort of there in the dynamics, but there's this sort of question about what's the minimal structure I need to sort of get the game going, and then I propagate the allowed trajectories.
I guess so from my point of view, the question about Simon's position would be, did he start off with a structure that was too minimal? That in some sense, in your view, you have more structure, and so you have something that adequately captures the space-time geometry, whereas he was trying to have a too minimal background geometry, and then you have to add in this other thing in order to have a well-defined dynamical theory.
Well, I suppose, except that he doesn't add it in by hand, right? You write down the dynamics in his minimal. I mean, you guys are all arguing that I was right in the first place. So I think we should get
I'm sorry.
So, we have a pretty long queue. So, Jim was up for
That was a hand.
Okay, good. And Mike?
Yeah, I think you're absolutely right that there are these two different space-time roles, and you can ask two different kinds of questions. Like, if you've got, especially it's clear in cases like here where you've got a theory with a dynamical metric in it, that then all other interactions coupled to that dynamical metric, you can say, well, what space-time structure do I need to write down the full theory? And in the case of GR, that doesn't have any metrical structure in it, it's just got the manifold structure. And then, though, you can also ask then, given that these other interactions universally coupled to this dynamical field, what structure is it that they're going to measure? And then it's that the space-time structure is that metric. Actually, I think I now understand what Simon was asking, because I added a section to my Harvey Fest paper that I'll send to you in response to questions from Simon. And in particular, he was asking about these sorts of weird theories that Brian Pitt is always going on about, where you start with a Minkowski background structure, you write down a tensor field on it, and then you couple other interactions to that field. So they're measuring this dynamical field, and there's a metric there. But unlike GR, the dynamical field that the coupling to might require some metric structure for
its definition.
For its definition. And and I said in that section I say, well, yeah, these are just two different. If you ask what's the space-time structure of the dynamics, you ask which dynamics. Is the dynamics in this background field, or is the dynamics of rods and clocks? And I think I'm a space-time functionalist. But I don't think that whatever we call the position, one should not be bothered by the idea that there are different, two space-time metrics depending on which dynamics you're talking about.
Excellent. Is there a question there? That all sounded wonderful.
There's a comment.
Yes.
But okay, actually, there's a question. Because I'm a little worried then about David's approach, because I mean, there is a way of getting to GR which starts with a background Minkowski metric. You write down the linearized field equations, put the stress energy of that in as a source term, and you get, you know, at the end of the day, you get the full field equations, and you find, hey, those are generally covariant. That background space-time structure that I presumed actually isn't needed for formulating the full theory, though it kind of looks like it. My worry is, maybe I should read David's paper, but why shouldn't I think that something similar is going on in David's paper, that background structure actually isn't physically significant?
So I'm taking it that he's going to think that you come to the correct background structure after lots of theory, you know,
Yeah, right.
that you cut out surplus structure in the usual way. So I think his response to that would be that, of course, it's not always obvious.
Right.
One of the things we definitely shouldn't think is that, and I mean, maybe this is, I mean, you know, sometimes when I'm ranting about space-time functionalists, I rant about the mathematical fetishist who thinks that whenever you've written down some mathematical structure, you've described the space-time. And I take it the kind of functional background geometry person is opposed to that as well. So it's not that just by kind of formulating the theory in a certain way, you've kind of thereby endowed it with the minimal geometry, right, that you need. The minimal geometry you need is something that's picked out by the dynamics of theory. It might not be obvious, and you might have to do a lot of processing to get to it.
Okay.
So I suspect that's what David would think about.
Valkyrie?
I just wanted to amplify one of the things that you were worried about earlier, and this is a bit of mathematical fetishism, so sorry. But so you balked a bit at formulating Maxwell spacetime in terms of equivalence class connection. And I think that there is a subtle question about how exactly you formulate that theory. So you might formulate with equivalence class of connections, or you might formulate it as a collection of models with the connections, and then say there's these extra isomorphisms in between them.
Sure.
That's the thing that you get rid of when you quotient into equivalence classes. So those are different theories if you're just flat-footed fetishistic, I suppose. And Jim's result isn't going to extend to the one that has the extra isomorphisms in it. And so there's kind of two options here. The physical upshot of this is that when you have like physical consequence of having these extra isomorphisms is that you're going to get funny stuff going on with boundary conditions when you impose them. You're going to get to asymptotic behavior. And so depending on which of these two you go with, David's point either is going to apply or won't. And it's also, I think, if you go the other way, then you, Saunders is saying, have the same mathematical models anyway. And so there's a subtlety in what exactly the Maxwell formulation is supposed to be that's also sort of impacting the other theories, I think.
Okay, no, that's very interesting. I haven't thought about that at all. I mean, the worry I was worrying about was just that there is something slightly surprising here about the fact that whether you write this down in, you know, coordinate formulation or, I mean, just it looks very unstable in the it looks like inherently like a bad theory in the differential geometry context, just because it just looks like it's crying out for you to select to pick a model. But I guess obviously one can be subtle about model equivalence in various kinds of ways. But yeah, I'm curious to hear about boundary conditions, but I should ask you about that later. I mean, you do need all of this stuff, you know, it turns out does depend on boundary conditions anyway, in ways that we normally don't just kind of see boundary conditions.
Bill?
I just wanted to remark about the reaction. A long time ago, was trying to suggest to Howard that the corollary 6 should be the fundamental thing, and not, and of course he's sticking to corollary 5. And one of his reactions was that you would need, if the openness of corollary 6 involves, you have, for all these accelerations, you don't have the third law of motion applying to the thing at the other end. And recently, George, of course, at the last PSA, or the one was giving that Newton was actually considering a possible one where the whole solar system is orbiting in front of some big thing.
Name of the Milky Way.
Yeah, but no, I mean a different kind of. At any rate, his fundamental reason, that at least when he was talking to me about it, was that you don't you really want to have a system that you can apply the third law of motion to all the and to have the acceleration and in this as it were just introduced accelerations are not, anyway, that's what he answered me with. And I don't know how,
So was his point that you need a sort of about sources for the gravitational field, or it's about the applicability of the, because I mean, an obvious thing to say when you go, oh, there's these symmetries, if you go, well, I just force all my gravitational fields to have a source.
what reminded me of it was your thing, the physics of the universe as a whole or something.
Yeah.
But you want to think of this as being able to take a system that you can regard as isolated,
Yeah.
and you don't want to, and so he wants, I mean, this is, look, I'm just
Yeah.
saying what he, you would want, and I'm not sure how much of this would be Newton as opposed to how we think of the theory, but Newton, you'd want to have, until you could have something that's think of it as
Yeah.
if you want to have the gravitation theory be doing it all.
Yeah,
Okay,
sure.
then you better, these accelerations are introducing something that needs something else before you've got the whole.
Yeah.
And I think that, no, I've said more than he said. He just said you need to have something. You don't have the third law of motion without, applying to these.
Yeah, maybe I'm gonna, this is the thing, because I had a similar conversation with Howard. Yeah, because I actually asked him, why didn't you go for the Newton-Cartan version of this? And it was basically that. If you've got this symmetry group that includes arbitrary accelerations, then those accelerations will be, basically it's like introducing forces without sources,
Yeah.
right? To which the third law doesn't apply. And Howard was very concerned about the very central role that the third law played in Newton's arriving at gravity, which we heard in great detail actually from George Smith. So that if you go to this wider formulation, there doesn't seem to be a role for the third law to apply to all forces, and then it's hard to make sense of the actual route to gravity. That was Howard's concern.
So I guess the sort of the standard move you might make there in response, right, is to talk about worry about infinite homogeneous Newtonian cosmologies, right? Where
well, that's not the concern, but
well, I mean, but if you want something that can model those, then you have to move away from the force-based formulation, and you're going to have to deal with some of these problems anyway.
Okay.
I mean, you could just say so much the worse.
So, Robert, you had a finger also? I'm going to give it a few more
just
minutes.
wanna say this-
I'm going to go a few more minutes because there's so many questions, and I thought it was such a great talk. So.
This
Yeah,
is
it's a great talk.
This is discussed in Stein's 1977 paper, exactly, and I also mentioned it yesterday, that Newton can't treat this as a relativity principle because he assumes, A, if there was an acceleration of a system from outside, there would be a source, but then B, nothing ever really behaves like in corollary 6, right? To a very good approximation, right, the differential accelerations can be ignored. But of course, no gravitational field acts exactly the same on two things unless they're at the same distance. And and it's not acting in parallel lines on anything unless they're in the same direction from the source. And so it's all approximate for Newton. And it's got to be part of an interaction with this long-range source that's accelerating the whole thing. On the other hand, of course, it still remains true that that you can't distinguish the dynamics of an isolated system from the dynamics of that same isolated system subject to a linear acceleration. So the idea that what started this whole debate, or not debate, but what started this whole investigation is, can you just articulate a structure that's weak enough that it doesn't distinguish those two cases? And I think Newton's objection about the third law applies with, it's a reasonable thing for him to think this is as far as I have to go, and there really is in principle a true inertial frame, but it doesn't affect this investigation now.
Yeah, no, that's fair enough. I mean, obviously, by starting with the rather particular Newtonian, very, very far away from Newton's formulation of Newtonian mechanics, when you move to it, you prejudice the debate in all sorts of ways, right? So you've already moved to a formulation where this kind of reformulation looks much more plausible than this.
Michael, is your question quick?
I hope so.
Okay.
So it's really kind of following up what has just emerged, which is really how do we relate this to the recent Newtonian relativity stuff, which is really about, as I understand it, how does Newton empirically apply his theory? I mean, how does he actually make it fit what we experience?
Yep.
That seems like a good answer to that. And you alluded to something like that, well, these things really are, for all intents and purposes,
Yeah.
empirically inertial frames. But nevertheless, there is a sequence of them, depending on how big the rotating system is that you're looking at. That's why I made that remark
Yeah.
about the Milky Way. And of course, that was
Yeah.
known to people very quickly. Of course, the whole solar system is falling
Yeah.
towards something else.
You actually do
but
everything
you-
just the way you do in GR.
yeah,
right?
but
But
you can
you-
abstract. You can
Yeah.
abstract from that. So, I'm really just asking, how does that kind of view, which is geared more toward how does Newton empirically apply his theory? How do you think of that? Since you mentioned that in passing, with this other thing about what's the right abstract space-time structure?
Sure. So I suppose I see the thought about how Newton applies his theory as a bolsterer for the idea that you can just find this inertial structure in the theory itself. Because, I mean, not only is it kind of there theoretically, but in fact it's the structure that we're really calling, in any operationalized sense, it's the structure we're treating as inertial.
Yes.
So I mean, I don't know how totally central that is to the argument. To me, that's a sort of strong motivator to think that it's not violence to the original Newtonian mechanics in a sense. To
When I
think of it in
talked to
this
Simon
way.
about this, I never quite understood what he was saying,
Yeah.
but I always said, but what is the empirical, how do we empirically apply the theory? What is the empirical meaning of the theory? And
Yeah.
that seems to go in a quite different direction.
Yeah. So the funny tension in Simon's thing is that he gives all this lovely detail about how he empirically applied the theory, and it constantly refers to freely falling frames. But I think because those are approximate, all of these things that are just referred to, I think Simon just takes that that's just the operational side of the theory.
Just the
Yeah,
operational.
exactly. I mean, I think that might be what's going on.
That's just the empirical meaning of the theory.
So, we've gone on. Is it really, really, really quick?
I just want to make sure everybody in the room knows something. Namely, there is a Proposition 42 in Newton's manuscript that was going to be added in the second edition as it was done in the 1690s, in which he identifies a force in which the system, our solar system, would be titanic. That is, he proves there exists a proper accelerative force under which our system is titanic. So Newton, whatever Newton did think, he thought enough through to see an external force could produce exactly that effect.
Yeah, it's really interesting. Thank you.
Does everybody know that?
I
It's
didn't know
not
that.
published yet. Okay, it's so widely out now that that's why I interrupted. I didn't know who knew it and who did not.
So I'm a weak chair. I will let Jim ask this question.
Well, it's not really a question. So I just want to remark that.
Oh, okay, it's okay. We're done.
No, that this business about how to formulate a standard rotation is a red herring.
Yeah. Okay.
So give me a smooth scalar field T whose gradient is orthogonal to next year, so I don't ever mention derivative operators that you don't want. Satisfies that for something that we would think of as a spatial metric.
Yeah, sure.
This thing is going to define something I'm going to write this way, which is a derivative operator on just space-like vector fields.
Okay.
Now, a standard of rotation is an operator that takes me from smooth vector fields to an object that I can write like this, which is antisymmetric, and which satisfies the following conditions. For any two vector fields, this holds. It's a derivation in this sense. And for any space-like, is a space-like vector field at a, yeah, so in a neighborhood, this equals space-like, then so this is this operator. I claim that any one of these uniquely gives rise to an equivalence class of derivative operators
Okay.
that satisfy the conditions before, and I haven't had to mention a covariant derivative operator anywhere. So Maximal Huygens spacetime then, in my sense, would be that.
That's exactly what I call the conformal derivative operator in that Weil-type theorem paper that I sent you a while ago that was wrong.
Great.
No, thanks, that's really helpful, because I've never known how to think about the rotation subject, so that's super helpful, thank you.
Okay, now we're really done, and let's just take 5 minutes and then go.